So now let's see a formal definition, right? So much like what we saw in the case of DFAs, NFAs, regular expressions, etc. So like always, my suggestion is to not be overawed by these definitions, but as long as you understand what is going on, that is good enough, right? You need to know the definition, but don't get lost in the notation. So one should have an understanding of what these definitions actually say, right? So a context-free grammar is a 4-tuple. Okay, so in a DFA we had a 5-tuple. V sigma RS, right, where V is the set of variables. Okay, so we already know what variables are. Usually this is represented by capital letters. Sigma is a finite set called terminals. Okay, and sigma is separate from V. It doesn't have any intersection with V. R is a set of rules, and each rule is of this form, right? So you have one variable in the left side giving a string of variables and terminals in the right side, right? So it could be something like, for example, A giving A, S, B, let's say A, right? So A giving a string of variables and terminals, right? So it could even be something like A giving, it could even be something like A giving small a. That's also a rule, right? The string could be a very short string, right? So R is a set of rules, and this R is a set of rules, and what I've written here is just 2 separate rules, right? And S is the start variable, and typically the start variable is the first variable, is the variable on the left side of the first rule that is listed, right? So you would list down the rules, you look at the first rule and see what is the variable that is replaced by the first rule, or what is the variable that is featuring in the left hand side of the first rule. That is the start variable. Okay. And one thing is, so even though I am calling it sigma is terminals, meaning they are like denoted by letters, small case letters, not capital letters, or numbers like 0, 1, etc., or it could be other symbols like open bracket, close bracket, etc. So these are terminals because they cannot be further replaced by something. Variables are variables, they can be replaced by something, and we don't know what rule is going to be applied. So in that sense, we don't know what is end product. Terminals means you have terminated the processing of them, and this is the end product, right? So this is not going to change, right? So even though we call them terminals, in some sense the end in some sense this corresponds to the alphabet that we saw in DFAs, NFAs, etc., right? So the string that is recognized, or the string that is recognized by the DFAs would be comprising of symbols from the sigma. Similarly, in a context-free grammar, in a context-free language, all the strings will be comprising of only terminals, because this is what we are looking for. Like, I don't want a string with variables in between. I want to replace all the variables by terminals using the rules again and again, right? So finally, I will have a string of only terminals. So sigma, the string that I have will be completely comprising of terminals, or the string will be a member of sigma star. So in that sense, even though in the case of DFA, NFA, we call them alphabet, and here we are calling them terminals, they kind of play the same role, right? And the strings that we generate in the context-free grammar is using will be part of sigma star. Okay. Okay. So even though I have not formally stated this, so this is a context-free grammar, right? I have not formally written this, but a context-free language, maybe I will just write it here. Right? A context-free language is something that can be generated using a context-free grammar. Maybe I'll just write it here. I'm just finding some space. a context we'll use CFL to denote a context free language is a language that can be generated from a context free grammar, right. So anything for which you can write a context free grammar for is called a context free language. So we already seen some examples. Okay, so now let's see what how you get a string from a grammar, right. So we already seen informally, let's just see formally. So one application of a rule is, let's say you have UAW, right. So this is a string containing one variable A and some other thing U and some other thing W, and we are replacing A with V, okay. So using some rule where A can be replaced by V, okay. So this is called yields. UAW, we say yields UVW, okay, and this is denoted by the single arrow, or not single arrow, that's double arrow, but yeah, double arrow, yeah. And we say derives, which uses similar notation, but it has a star over the arrow, right. You say U derives V if starting from U there is a sequence of replacements that we can get such that, so where U is U1 and UK is V, right. So U is U1, and from U1 you get U2, and from U2 yields U2 yields U3, U3 yields U4, and so on. Finally, we UK minus 1 yields UK, which is the same as V, right. Such that so basically it is just this, starting from you must be able to use the rules again and again and successively yields strings till we get V, right. So we say U derives V if we are able to repeatedly use the rules to get V, right. And like U and V could be general strings consisting of variables, terminals, combination of both, everything. But the language of the grammar, right, is a set of strings that you can obtain that consist of only terminals, right. So once again, the language of the grammar is a set of all W that can be generated, right. So notice that W that can be generated using only the terminals, right, W from sigma star, such that starting from you can get the W starting from the starting variable, right. So you start from the starting variable S and are able to repeatedly apply rules till we get W. So the language is the set of all strings that only consist of variables, only consists of terminals and can be derived from the starting variable, right. So we have seen enough examples already. And just to quickly tell why is it called context free? The context free because the rules are defined like this, right. So the rules are something like this: A gives this, A gives epsilon, A gives small a, capital A gives ASA, or S gives ASB. So this is all we are saying things like S gives ASB, right. So we are telling how to replace S. We are not and it doesn't matter what is to the left of S or what is to the right of S. S is going to be replaced by this. So think about the other situation where, let's say we have rules like this. Suppose we have rules like this. So A, V, B, where V is some variable. So now we see that V has A to its left and B to its right. And now if that is the case, we replace it V by X. So now we get AXB. However, we had B to its left and A to its right. Suppose it was of the form BVA. Then you replace V by Y. right? So here what I have written here is an example of rules where we look at what is there to the left and right and then tell what to replace it with. Meaning I am looking at the context in which the variable is surrounded, the context in which the variable is situated, context in which the variable is seen, to determine which rule applies to the variable, right? So this is what you would call context sensitive languages, right, or context sensitive rules, where I have to look at the variable and look at the context in which we saw them. However, all the variables and all the rules that we saw so far in the case of context free languages or context free grammars do not look at the context. They're just saying that you see a v, right, and then v gives a x y or something like that, right, without really, or v gives x, right, without really bothering about what is v surrounded by. So that is why this is called context free grammars. The rules and the productions are independent of the context in which the variable is found, hence it's called context free grammar, right? So rules do not depend on the context in this case. There are cases, or we can form grammars and languages where we bother about the context, right? So this is called context sensitive grammars or context sensitive languages, etc. However, we are not going to be covering them in this course, right? So in this course we will only be looking at context free languages, right? So this is the reason for the nomenclature or the name context free grammar. Now let us see. So I said earlier that we will see why properly nested parentheses or properly nested brackets are a context free or is a context free language. So let's see why. So this is the grammar. The grammar has only one variable s and two terminals small a and small b. So I'm just using a and b instead of open bracket and close bracket just because ease of writing. And there are three rules. In fact, R is consisting of three rules, but I'm just writing them like this in shorthand, a bit of shorthand: ASB or SS or empty string. So let us see some situations. So S gives ASB, again S gives ASB. Let's say S gives empty string, so you get AABB. Maybe S gives ASB. Oh, sorry, I'll use another starting rule. I'll use S gives SS. Maybe now there are two S's. Let us deal with the first S, ASBS. First S again, AASBBS, AABBS. Maybe I'm just going to come over here. So AABB, AASB, AABB, AB. So here also the resulting string is, I'm just highlighting the resulting string, AABBAB. The first time we got AABB. So you can see two strings in both the cases. So if you replace A with open bracket, so you get, and B with closed bracket, you get this. And you can see that this is indeed properly nested parentheses or properly nested brackets. And in fact, you can see that any string that consists of properly nested brackets can be generated using this, right? So you come up with anything. So the vague or the high level idea is the following, right? So either the string is of this form, right? So the starting has to be an open bracket. You cannot start with the closed bracket, right? Because if the starting is with a closed bracket, then you are not properly nested anyway. If the starting string open bracket if the partner of that open bracket is the very last symbol, right, and the rest of the string is something in between, right, then it is like we are using the rule ASB. S gives ASB, right. However, if the partner close bracket was in the middle somewhere, right, and then there is again an opening bracket and again a closing bracket, then it is like we use the rule SS to begin with. So this is a high level idea, but it can indeed be verified that this generates all the strings that correspond to the properly nested brackets, right. So it's a very simple context free grammar, only one variable S, only two symbols A and B, right, and three rules. S gives ASB, S gives SS, and S gives empty string, right. Right. So this is yet another. So we already saw 0 power n, 1 power n, which is not a regular language but is a context free language. And now we have the set of all properly nested parentheses, which is not a regular language but is a context free language. Now let us see some simple observations. We have already seen some observations, but now let us see two more. Suppose A and B are two context free grammars. So I am saying A and B be the two context free grammars. And meaning we have separate set of rules, etc., right. So A generates some language and B generates some language. Now can we design a grammar that generates the union of whatever A generates and whatever B generates, right. So we know that union is a regular operation and regular languages are closed under union. Is it true for context free languages, right. So you have some grammar A which has some rules, right, say some SA, let's be the starting thing, some other thing, X gives something, Y gives something, etc. And similarly you have SB be the starting variable, let's say some P something, right. Now can we construct a grammar that generates a union set of strings? The answer is yes. It's very easy. You create a new, you combine the rules of both A and B. You create a new starting variable which you call S. So S is called a new starting variable. This S, right? S is a new starting variable, and this S produces either SA or SB, right. So this is two rules, S yields SA and S yields SB, and then you have all the rules of A and all the rules of B. So now either S can yield SA and then with SA can yield any string that is generated by A, or S can yield SB and SB can yield any string generated by B. So this is how we can get any string generated by A and B, which meaning the union language, right. So context free languages are also closed under union, right. That's the learning here. CFLs are closed under union, right. Okay. Now we already said that this is a bit more than regular languages, but we also saw examples where there were languages that were not regular but are CFGs. But every regular language, can we express every regular language using context free grammar, right? Meaning, are regular languages a subclass of context free languages, or a subset of context free languages? The answer is yes. Every regular language can be expressed using a CFG. So let's see how. So the way to do it is you have a DFA. You start with the DFA. If a language is regular, there is a DFA, right? You consider, you start with the DFA, you have one variable for each state of the CFG, right? And then corresponding to each transition you have rules, and that gives the that gives us the grammar. Let's see in this case. So this is a DFA. In fact, the language that is recognized is all the strings that contain 0, 1, I believe, right? So let's see what are the things that, so we need three, so there are three states here, small a, small b, small c. So correspondingly we will have three variables, right? In this case, three variables, capital A, capital B and capital C. Now let's see what are the rules. So let's say capital A corresponds to the state small a. So if there is a rule delta QIA, okay, so there is a small issue here because I am using A for the alphabet in the case of a DFA, and here A is called a state. So maybe I will do a small change. So I will call it QA, QB and QC. Okay. So QI comma A equal to QJ. Maybe I'll make it further simplified. So maybe I'll say R or something. Okay. So QIR equal to QJ gives us VIR to VJ. So the rules here are, so A gives, so when you, upon seeing a 0 you go to B. So the corresponding rule is 0 and B. And upon seeing a 1 you go to itself. So you have 1A. So A yields 0B and A yields 1A. And similarly B yields also 0B, because upon seeing a B from 0 or upon seeing a 0 from B you go to itself. Upon seeing a 1 you go to C, right? So 1C. And C, upon seeing a 0 you go to C, and upon seeing a 1 you go to C. However, you notice that this is not a complete context free grammar, because this will on the right hand side of every rule there is always a variable. So this is not going to help. So where are we going to get rid of variables, right? So for that purpose we have this final set of rule here. So whenever there is a state which is an accepting state, we will add, if Qj is an accepting state, we add Vj yields empty string. So here Qc is an accepting state, so we add C yields empty string. So now you can try playing around and seeing what this context free grammar yields, right? And this will yield the exact same set of strings that this DFA accepts, nothing more, nothing less. So so either you can verify that this yields exactly the set of strings, which is the set of all strings that contain the substring 0, 1, right? So so this you can verify. So far we have seen context free grammar, we have seen examples, we have seen the definition, we have seen why they are interesting, we have seen what is called the parse tree, right? We have seen the formal definition, we have seen what are the set of strings that is derived from the context free grammar, right? We saw these things that context free languages are closed under union, and we saw this thing that all regular languages are expressed using context free grammars. So whatever we did here is something general. So given any DFA, we can write a context free grammar that such that this context free grammar generates the same language as the DFA, right? So finally, there is one more small concept that I wanted to just quickly talk about before closing the lecture. This is called ambiguity. Okay, so ambiguity means like confusion or uncertainty. Let's see, right? So suppose we have a grammar like this, right? So the grammar is there is only one variable, right? So one variable E, and terminal, there are multiple terminals. There is a small a, there is a plus symbol, there is an x or multiplication symbol, there is an open bracket, and there is a closed parenthesis, right? So there are 5 terminals, and there are 4 rules. E gives E plus E gives E into E gives open parenthesis, E close parenthesis, and then E yields A. Now let us try to see 2 derivations of this grammar, right? So one of them, if you see the left hand side, this one, right, the one that I have drawn in red. So E first yields this EXE, and the E in the right side gives A, and the E in the left side gives A plus A, right? So here we get the string A plus AXA, A plus A multiplied by A, right? Whereas in the derivation in the right side, denoted by blue, right, the first rule is E gives E plus E, where the E in the left side gives A, and E in the right side gives A multiplied by A. So in both cases we end up with the same string, A plus A multiplied by A, right? However, the one in the red, the one in the left side, the multiplication happens at the last, right? So the multiplication happens at the top level, whereas in the one in the right side, where in the blue color, the addition happens at the top after the multiplication, right? So both strings have been generated from the same grammar, but both of them are the exact same string also, right? So it's the same string, they're generated by the same grammar, but in 2 completely different ways, right? So even if you look at these trees, they're structurally different. So here the X happens at the top level, and here the plus happens at the top level, right? So if the X happens at the top level, it means that the X has precedence, the multiplication has precedence. Sorry, the X happens after the addition, whereas the plus happens at the top level means the plus happens after the multiplication, right? So the precedence really depends on which happens first, right? And this has to be actually included in the grammar. But if we just see the string A plus A multiplied by A, so think about a computer program, right? You're writing code. Let's say you write 6 plus 10 into 5. 6 plus 10 multiplied by 5. You are just writing it in the code, or x plus y multiplied by z. Now when the compiler reads it and interprets it, how should it interpret it? Either the plus should happen after the multiplication, or the multiplication should happen after the addition, right? Okay, so it depends on how the grammar is defined. But one thing is clear, it is not desirable that the same string x plus y multiplied by z, both of them are possible. Like if this is the string that you're reading, it should not have 2 different meanings, because that will give the compiler some confusion, right? So depending on what number system you are working with, perhaps multiplication takes precedence over addition, or perhaps the opposite. But it is not desirable that the situation is unclear. So you want the situation to be quite clear as to whether addition takes precedence over multiplication or the other way around, right? So what is the issue here is that it is not clear which one takes precedence, or in other words, it is not clear in which derivation was used to generate this or produce this string A plus A multiplied by A, right? So this is an undesirable situation, and this undesirable situation is called ambiguity. So ambiguity is by definition, ambiguity means that the same string can be generated in two different, structurally different ways, which is what is happening here, right? So even in English sentences, sometimes this confusion can be there, right? But English is a natural language, and sometimes these uncertainties can be there, and somehow, let's say for instance this sentence, let's say she called the man with an iPhone, right? So is it that she used her own iPhone to call the man, right? So she called the man with the iPhone, so she is using the iPhone to make the call to the man, or is it that with an iPhone is an adjective of the man? So there are several men, and she's calling the man who has the iPhone, right? So the same sentence has two different interpretations. But in common natural language conversations, there are contexts perhaps, or perhaps you can end up asking the other person. Usually the exact precision is not there, but that is somehow, usually it gets clarified through interaction, because usually common language, you keep talking, it's a conversation. Whereas in computer program, it's not like the computer program can always come back and ask such questions. It's like you want precision, you want clarity, you don't want this confusion, right? So this is called ambiguity. This confusion is called ambiguity, right? And it is not a desirable thing to have, right? In some cases, not in all cases, in some cases we can actually take the grammar and modify it to get rid of the ambiguity. So for instance, the grammar that is written here, the one at the top, right? I am talking about this underlined grammar. This grammar that I have underlined here, right? This generates some set of strings. The grammar that I have written here, this also generates the same set of strings. However, this one does not have ambiguity because it has a different set of variables. So here E can be replaced by E plus T, where T stands for a term, and then T can be replaced by T multiplied by F, where F stands for a factor, right? So a multiplicative factor will come after, the addition will come after the multiplication. So multiplication clearly takes precedence here. And of course, there is always this provision for this parenthesis here, right, which we had here also, but we didn't end up using it. So you can verify that this grammar generates the same language, and you can also verify that this particular kind of ambiguity does not get reflected here, right? So this issue is called ambiguity, and this is not desirable, because in a computer program you want to communicate with clarity as to what the operation, what is the addition or multiplication has to be performed. So just a brief point about leftmost derivation, right? So leftmost derivation means you always expand the leftmost variable, right? So sometimes when you have a string of multiple variables, you expand the leftmost variable. So just quickly, so you have a very brief grammar here. S gives AB, A gives small a, and B gives small b. So you could do this: S gives AB, you replace the A with small a, and then you replace the B with small b. Or you could replace the B first and then the A. But both of them are stuck. So what I am saying is, there are two different ways to derive small a, small b, but the only difference is that I am applying the rules in a different order. In other words, if I just try to draw the tree here, so it is like this: S gives capital A, capital B, capital A gives small b gives small b. The same tree applies to both of these derivations, right? So suppose I had insisted that I always expand the leftmost variable first, then the second derivation, this derivation will be the only one that meets that condition, right? Because here we have A and B, and sorry, not the second, sorry, only the first one will meet that condition. Right? We have A and B and we replace A first. So, suppose I say that the leftmost variable always has to be replaced, then there is only one way to derive AB. However, here that was not the case. Even with the same leftmost derivation, there are two different ways to get it. So, that is why we have two different trees also. So, a leftmost derivation corresponds to a certain tree. So, here both the derivations correspond to the same tree, right. So, I am just defining this leftmost derivation just to define formally what is ambiguity. So, we say that a string is derived ambiguously if it has two or more distinct leftmost derivations. So, this is an example. A plus A multiplied by A has two or at least two distinct leftmost derivations. So, here the E gets replaced by E multiplied by E. In the right side, E gets replaced by E plus E, right. Here E, on the left side, E gets replaced by E multiplied by E first. Here it is E plus E first. Right. Now, even if we do everything leftmost, they are structurally different. That is why the tree is different. Right. So, a string is derived ambiguously in a grammar, in a context free grammar, if it has two or more distinct leftmost derivation. And the grammar, we say that the grammar is ambiguous if it generates some string in an ambiguous manner. Right. If there is some string that is generated ambiguously, we say that the grammar is ambiguous, right. So, that is the definition of ambiguity, which is not a desirable trait, right. So, I will quickly summarize this lecture. So, we introduced context free languages. We said that there are two representations using push down automata and using context free grammar. We are going to see context free grammar. We defined context free grammar. We saw some examples, right. We saw that we saw which are the strings that are generated from the context free grammar. We saw what is the language that is generated from the context free grammar, right. We saw why it is context free. We saw that regular languages are context free. We saw that context free languages are closed under union, and then we saw ambiguity, and we formally saw the definition as well. And with that, we will close week 3. In the next week, we will see more on context free languages and context free grammars. We will see other ways to represent them and other rules that pertain to them. Thank you.